Okay, guys, so I'm making the video on a Saturday afternoon. Very miserable out there. I was hoping for some sun this weekend, but no luck. So today we're gonna learn about trigonometric equations, solving them, and because we've taught the identity material first, we'll actually be able to use some of that today to solve some of the questions, not all of them, but some of the questions are very much what you would have done last year and grade 11, with the main difference being that in as far as the angles are concerned, we'll be working in radians. So our answers will be things like pi over 3 or 5 pi over 4, as opposed to like 60 degrees and maybe 315 degrees or something. Okay, so let's just go back a bit though, because I think trigonometry is one of those areas in math where, I mean, you've been working at it for probably 3 years, 4 years since you first learned about trigonometry. And there's a lot of stuff you've learned over the years, try to compartmentalize it. And so I kind of refer to this sort of as our toolkit, kind of the things that if you didn't know about trigonometry, then this level of math just wouldn't be for you. And if you're planning to go on to post-secondary, some of you, this will sort of be the end of your trigonometry journey. But for some of you, you'll be going into areas where you actually go even deeper into this and look at the complex number plane and polar coordinates, and even when you get into some engineering stuff, how all this kind of ties in at that level. So I'm going to just do a quick review of things that you should know before we jump into today's lesson. So sine, cos, and tan, that's kind of where you started your journey. And most of you remember, I'm sure, SOHCAHTOA. It seems like so long ago now. And that's really sort of looking at the triangle in terms of a right angle triangle where you have like a hypotenuse, maybe an angle theta, opposite side and adjacent side. And you can write all the trig ratios based on your SOHCAHTOA rule. You know about the Pythagorean formula, a squared plus b squared equals c squared. And then when we get into angles in standard position, we start looking at angles that are far bigger than 90 degrees, which would kind of rule this triangle out for the most part, because that triangle theta could only be less than 90 degrees. So when we look at the coordinates, we have pi over 2, we have pi, 3 pi over 2, 2 pi, and of course the quadrants 1, 2, 3, and 4. And we know that sine now is y over r, cos is x over r, and tangent is y over x. Then, of course, we get cosecant theta, which is just the reciprocal of sine, so it's r over y. We get secant theta, which is the reciprocal of cos, which is r over x. And then we get cotangent theta, which is the reciprocal of tan, which is x over y. And if we rearrange the Pythagorean formula, we get x squared plus y squared equals r squared. So I'm hoping that kind of rings some bells for you. And then, of course, we have our ASTC rule, and that's the rule that lets you know where the trig functions are positive and also where they're negative. So, for example, something like sine, we know that sine is positive in quadrant 1 and quadrant 2, but it'd be negative in quadrants 3 and 4. And if you had secant, well, that's just cos flipped. So we know that secant should be positive in 1 and 4, but negative in quadrants 2 and 3. Anyway, so there's a lot of different things I could go over here. I guess one more thing I'm going to just review with you is what we learned last chapter, which is the sine curve has this general shape to it, and the cos curve has this shape. And maybe I'll put some numbers in here: pi, 2 pi, 3 pi over 2, and pi over 2. That's 1, that's a 0, and a negative 1. 1, 0, negative 1, pi over 2, pi, 3 pi over 2, and 2 pi. And once again, just to reinforce that, we said that cos was positive in quadrants 1 and 4, and we can see that here. That's obviously positive, and that's positive. And in quadrants 2 and 3, it's negative. And same with sine. Sine is negative here and here, and that's quadrants 3 and 4, but it's positive in quadrants 1 and 2. So once again, that's just some review of the things we've learned, and you've learned lots more than that, of course. But I think that's a good starting point to go at. So with this kind of weaponry in our heads, we can answer lots of cool questions about trig equations. And I'll start off with sort of an easier one first here. So let's try something like 2x or 2 sine x minus 1. Let's just go plus 1 equals 0. And you're told to solve it over the set 0 is less than or equal to x, which is less than 2 pi. And that would be our first question. So you're told that. Now notice that we're working in radians here. So even though you might convert to degrees, although I think that is a lot of time wasted if you do that, your final answer has to be in radians. So if you just leave it in degrees, I won't mark it right, because by this stage of grade 12 math, you should be able to work in radians. So I'm going to solve this problem completely in radians and not convert to degrees at all. I think if you've done well in the last unit, then this should kind of make sense for you. So I'm just going to give you some steps here to solving these questions, and I would really encourage you to follow these steps. They're actually very similar to what we went over in the chapter before this. So the first thing I would do is I would sketch theta, or the angle. In this case, it would be x, I guess, but theta, the unknown angle. So right now I've got 2 sine x plus 1 equals 0. And I don't really, just looking at that, that might be unclear as to where theta would be. That is using your ASTC rule here. So the first thing I might do is rearrange the equation so I can sketch theta. So let's rearrange this thing. So I'm going to bring the 1 over, so I'm going to subtract 1, and I'm going to divide by 2. So that's going to give me sine of x equals negative 1 divided by 2. Okay. Now, remember, for the most part, almost all the questions I'm going to give you are non-calculator based questions. And although, I mean, you can obviously, be sneaky and use your calculator to check your answers, all the work I mark you on is going to basically be non-decimal numbers. So you can't be showing decimal numbers through your work. So just to show you how I would do this, so I'm not using a calculator right now. You have to kind of believe me on that. Is I would sketch angle theta. So I'm just going to draw my little grid. And I'm going to use blue for my terminal arm. So I know the angle is producing a negative ratio, which means I have to be in quadrants 3 and 4, because that's where sine is negative. So it's got to be down here, and it's got to be over here. So I could have an angle that's bigger than 180 or bigger than pi, and I could have an angle that's bigger than 270 or 3 pi over 2, but less than 360, which is the same as 2 pi. So there's 2 possible answers I have here. And now what I'm going to look at is the fact that I have these numbers given to me. So that gives me some more information where I don't need to use a calculator. So I know that sine is y over r. So that would mean that the y value is negative 1 and the r value is 2. And currently I don't know the x value, although I know I can figure it out pretty quickly, but I don't really need it for this question. So I'm going to sketch my reference triangles. So I'm going to look for my step 2 here, which is to find reference triangles and also the reference angle. So the angle itself, okay? So to do that, I'm going to draw the y value here now. So I'm going to say that this distance here would be y, this distance over here would be y, and that according to my calculation, I did actually make a mistake here. This is negative 1, because it's negative 1 in the sign. So this side here is negative 1. This side here is negative 1. And I know the r value, the radius is 2. So that's 2. And that's a 2. And once again, I could easily figure out my x value, but this triangle I know is special. Actually, I know it's special for 2 reasons. One is I was asked to solve it without a calculator, but more importantly, I recognize these numbers. This has got to be the 1, 2, root 3 triangle. And so if you were to work out the x value, you would get plus and minus root 3. So it's the 1, 2, root 3, and I probably should have written up here, you should know those things. So I have a 60-degree angle and a 30-degree angle. That's 2, that's 1, and that's root 3. Okay. And so I know that the angle right here, the reference angle, is the same in both. It's the same triangles. So the reference angle would have to be the angle across from the 1. And so that's the 60 degrees. But remember, we're working in radians, so that's pi over 3. So pi over 3 is actually 60 degrees. Okay, so let's find our first theta then. So let's say that this theta, the smaller one, we'll call that theta 1, and we'll call this theta theta 2. Okay, so we have theta 1. Well, that is half a turn plus the reference angle. So maybe put these numbers in here. That might help us. That's pi over 2, 3 pi over 2, and 0 or 2 pi. Okay, so to get theta 1, I would say I'm going to go pi. I'm going to do half a turn, but I'm also going to move the reference angle, which is pi over 3. And now I add these numbers together. So I need common denominators. So 3 over 3, same as pi, plus 1 pi over 3 is going to give me 4 pi over 3. So that's one of my angles in the diagram. The second angle is done very similarly, is I'm going to take a full turn, 2 pi, and I'm going to minus the reference angle, that little green dot there. So I need to have common denominators, so it looks like I'm 3's again. So 3 times 2 makes this a 6 over 3, and 6 minus 1 is 5 pi over 3. Okay, so let's say they're looking at a second question. They give you the same problem, so same initial equation, give you this equation, but instead of saying 0 to 2 pi, they say write the general form. Or they might even say general solution. Now, what that means is they want you to find every single angle that this would be true for, okay? Now, to show you why this could be tricky if you try to literally write out every single angle, is that if you think about the sine function, we know it does this kind of turn, right? That's the sine function. And of course, if this is 1 and that's -1, then -1/2 would have to be down here. You can see you're getting your 2 answers in the third and fourth quadrants here. Now, and those, of course, are the answers we just wrote, the 4 pi over 3 and 5 pi over 3. But what we do also know is that the graph continues and continues again and again and just keep on going. And it actually even goes backwards. It repeats backwards. So if you extend that red line, how many intersection points are you going to have if you draw the entire sine graph? Well, just in this little diagram, I'd have 1, 2, 3, 4, 5, 6, 7, 8 approximately. But if I kept drawing this thing, there'd be an infinite number of solutions. So you could just literally write forever. Like it would take you forever, and then like your grandchildren could start writing them out, and then their great grandchildren could write them out, and they actually would be no closer than you were because there's an infinite number of solutions here. So we want to be able to write this quickly without saying this is a waste of our time. So what do we do here? Well, we take our first answer, 4 pi over 3, which is this one. This is 4 pi over 3. Okay, and then to get to the next one, to go to this one, that would be a distance of pi, because sorry, distance of 2 pi, because that is the period of the function. So basically to go up and then down and back, that is one period of the function. So one of my angles would be 4 pi over 3. And then I want to add 2 pi to get to the next one, and then another 2 pi and another 2 pi. So I'm going to say 2 pi n, where n is an element of I. And that would give me every possible answer using 4 pi over 3 as my start point, and then moving a distance of a period every time to get the other ones. And then the second angle would be taking 5 pi over 3, adding 2 pi n, where n is an element of I. And so these would be the general solutions that we would get here. Okay, so let's try another one kind of similar. And let's try example number 2. And we'll use cos of angle x plus root 2 equals negative cos of x. And we'll do the same thing. We'll do 2 different solutions. We'll do one from 0 to 2 pi. And then we'll also solve for a general form. Once again, if you want to pause the video and try this on your own, that might be a good way to see if you know what to do. But if not, and before I do, I'm going to just finish my rules here. I kind of just stopped writing steps here. So first thing I'm going to say is find your angle where it could be using your ASTC rule. Then we said find the reference triangle and the reference angle. And then the third step was find X, Y's, and R's. Well, you don't always need all three letters. Maybe just two is good enough. But if you get all three, then you're going to be for sure laughing. And number four, once you find that, you're going to want to try to solve the question. Okay, and there's a few different kinds of solving you could do here. Like once again, we solved for a general solution, and we also solved for a finite solution over a fixed interval. So let's solve this over the fixed interval first. So once again, I think what you're going to want to do is get your cos expression by itself. So I've got coses on both sides. So let's bring the cos to the left side. Delicious coffee. So I'm going to go cos x plus cos x gives me 2 cos x. And I'm going to subtract root 2 from both sides. So I get negative root 2. Divide both sides by 2. And I get cos x equals negative root 2 over 2. So this root 2 business, once again, that does seem familiar to me. If I go back to my things I should know, I probably should have also written in the other special triangle, which is the 1, 1, root 2. And that's the 45-degree triangle. And so we got a root 2 here. So I'm thinking something to do with 45 here. Now, this could be a little bit trickier to see this. I'm not sure why my computer won't let me. What's going on? No, stop doing that. There we go. Okay, so let's deal with the negative part first. So I'm going to be in quadrants 2 and 3. That's where cos is going to be negative. So I'm going to have an angle here. And I'm going to have an angle down there. So 2 different angles here. And let's see here. Well, this is telling me that my x value is negative root 2. And my y value is unknown. But my r value is going to be positive 2. Okay. Now that's a bit tricky, but let's put that on the diagram. Let's see what happens here. Okay. Okay. So let's look at this root 2 over 2 business here. So I want to just talk about that for a second. If you were to take the cos of 45 degrees, what you would get is an x value that's 1 over an r value that's root 2. You might remember back in grade 10 and grade 11, we said we don't leave radicals in the bottom of a fraction. So you would actually rationalize this number here. So to do that, we would do root 2 over root 2, and that actually gives us root 2 over 2. So the expression 1 over root 2 and root 2 over 2 is actually the same thing, which means this is a 45-degree triangle. So I can say that this is 2 and negative root 2. And of course, the y values would also have to be root 2's then, a negative root 2 and a positive root 2. But what's more important is that this angle here and this angle here are the same angle. And so that reference angle is actually equal to pi over 4. So that's what 45 degrees is here. Okay, so let's erase all this work so I can do a little bit more work in this area. So what I'm going to do is solve for the first angle. So I'm going to say theta 1 would be pi. That's where pi is right there. Pi is right there. So I'm going to go pi minus the reference angle, right? So pi minus pi over 4, and common denominator 4 is here. So I get 3 pi over 4. Okay, and then theta 2 would equal, where are we here? Well, we're in quadrant number 3, so we're going to go pi plus the reference angle, which is pi plus pi over 4. So once again, 4 over 4 plus pi over 4 is 5 pi over 4. So there's our 2 angles between 0 and 2 pi. So that'd be like question number 1. Now the general solution is basically finding coterminal angles. So we would say theta 1 is 3 pi over 4. Now what I want to do is I want to get back to that place. I want to go around once to get back there. So I'm going to add 2 pi n, okay? And n is an element of I. And then I go theta 2. Well, that's going to be your 5 pi over 4, the second one you found, plus another rotation, plus 2 pi m. So there would be your general solutions for those two kinds of questions. Okay, let's take a look here. Okay, so let's try just a few more. We'll do maybe 2 more, and I'll do another video in a day, maybe just to give you some time to kind of think about these questions, because it does take a bit of time to get your head around them. But I think if you did well in Math 11, you would have seen a lot of these questions then, but they would have been working in degrees. Okay, so here's a question that definitely I think is a bit more tricky. Sine x tan x equals 2 tan x. And let's just do the solution from 0 to 2 pi, and then we can just sort of narrow the question down a bit here. So we'll just solve it for, I guess I should have been writing that, solve for x. And how would we tackle that? Well, once again, I think when you see these kind of questions, it's very tempting to divide by numbers and just try to get rid of things, and that seems to make people feel good. And so let's say you had something like AB equaled 2B, okay? And you said, okay, well, there's B on both sides. I'm going to divide by B. And you're like, that's awesome, because look, now I get A equals 2. So A is 2, okay? Which kind of makes sense. If you put a 2 in for the A on the left-hand side, you would get 2B equals 2B, or not 2B. Oh, yeah, 2B. So we have AB, and that's going to be 2B equals 2B, and so there we're happy, okay? The problem is you divide it by B, and you don't know what B is. So let's say B was a number it can't be, then you wouldn't allowed to be doing that, I guess, right? Is that pretty cryptic for you? Okay, here we go. Try this. What if B was 0, and you said I'm going to divide by 0? Well, you wouldn't be allowed to do that. So the problem with dividing by a variable like this, you wind up losing answers along the way. So what you should have done is brought the B over. So subtract 2B from both sides. And if you solve that, you'd say, well, I could factor here. I could take a B out of all this. And that would give me B times A minus 2 equals 0. So I still would have gotten A equals 2. So I wouldn't have lost that. But what could this be so that when you times it by a number, you get 0? Well, that means B could be 0. So there actually would be 2 solutions to this, one where A is 2 and one where B is 0. So you want to really avoid the temptation to divide by common terms. You should really bring things over and factor them and then see if you can work with that. Okay, so this question has tan on both sides, so I'm going to bring tan, actually all my trig terms to the left side. So I have sine tan x minus 2 tan x all equals 0. I'm going to factor a tan out, so I get tan x times sine x minus 2 equals 0. Okay. Now, what I'm going to use now, it's called the AB rule. You would have been taught this in grade 11 math. And that is, if you have 2 numbers and you multiply them and they give you a 0, then one of 2 things, or actually 3 things, is possible. One is A is 0, B is 0, or both A and B equals 0. That's the only possible thing that would have could have happened here to give you a product of 0 when you times those numbers together. So what does that tell us? Well, that tells us that tan x equals 0, or sine minus 2, sine x minus 2 is equal to 0, which means sine x is equal to 2. And now what you have here are 2 separate trig equations you have to solve for, at least try to solve for, and see what happens. So maybe pause the video and see what you think about how you would do that. Okay, so I'm going to take a look at the tan one first. So tan being 0, so let's think here a second. Now, I did show you a fancy dancy thing using identities for this, but I'm going to avoid identities here because I think I can do this pretty quickly just thinking about tan. And so what I'm thinking about here is I'm getting a value of 0. And tan is x over y, which means the x values have to be 0. So I don't think I want to consider either of these two triangles that we've been working with. So we have, this or that. Or the other thing we should maybe look at is the unit circle. And the unit circle has these 4 really nice coordinates on the graph that we can work with to solve any question that lands on one of these places. That is pi over 2, oopsie, pi, 3 pi over 2, or 2 pi, or any coterminal angle to them. So I'm looking for the place where the x values are 0. So notice on the unit circle, let's go back here. On the unit circle, if I was to just do a quick sketch of the unit circle, my x values have to be 0, which means I have to be on the y-axis. That's the only place on the graph where the x values would be 0. So I could be at pi over 2, or I could be at 3 pi over 2. So this particular question would have 2 answers. One is pi over 2 and 3 pi over 2. Now the other one, it says when is sine of x equal to 2? Okay. Now once again, many ways you could do this. You could deal with this as a grade 12 student and say, well, I know sine looks like that. That's a 1, that's a 0, and a -1. And what Mr. Teacher is asking me is, when does the line at 2, when does it intersect the sine function? Well, it never does. It never goes through there. Another way to look at this would be also as a grade 12 student, say that sine is y over r. And so really you have 2 over 1. But what was r standing for? Well, r was the radius of the circle. And so what you're saying is the y value is larger than the radius of the actual circle. So that's not possible. And a third way you could think about this is as a grade 10 student and thinking, well, if this is angle theta, and this is the opposite side, and this is the hypotenuse, then the sine of theta would be the opposite over the hypotenuse. And you're saying it's 2 over 1. And you might remember back in grade 9, you were told that the hypotenuse is the longest side in a triangle. So what you're saying is the opposite side of this right triangle is larger than the hypotenuse. And if you could draw that for me on a 2-dimensional surface, I'll give you $100, okay? That is if it's accurate, okay? Okay, so that's not possible. So there's no solution for this one, no solution. Okay, so sines cannot be bigger than 1 or less than -1, just as they are right there. Okay, so there's a question for you. So let's see if we can move on here. Yeah, one more type. I'm going to deal actually just do 2 more types, and then we'll call it quits. So one is a what we call a second degree trigonometric equation. Now it sounds awful, and it kind of is a little bit awful because you got to do a bunch of different things here. But one is it's trigonometry, so you're solving for angles, and that's pretty at this point, I think pretty straightforward that we're doing that. But what does second degree mean? Well, second degree means like a quadratic. So you're dealing with a second powered trig term, and you're trying to solve for the trig term. So you kind of got the quadratic part here at the beginning. So you got a quadratic part, and you got a trig part. So 2 parts. So it's usually a benefit to try to do this in 2 separate stages here. So I'm going to deal with the grade 11 quadratic part first, and then the trigonometric part second. So doing these things as 2 separate things here. So here's the question. So the question is solve for secant squared x minus secant x minus 2 equals 0. Okay, and we'll do a general solution for this one. Okay, Now, I'm going to show you a technique here that you don't have to use, but I think some students like to use this because it simplifies the question for them. And it's using a substitution technique where what I'm going to do is I'm going to let the letter A equal the secant of x. Now, once again, you don't have to show it this way. I just think it makes it simpler to take a look at here. So secant squared x would be a squared then, because secant of x is a. And I'm going to minus an a, and I'm going to minus a 2. And in doing that step, we basically make this no longer trigonometric. It's just in a quadratic right now. So quadratics can be solved many different ways. So if you want to bust out the quadratic formula, you can fill your boots. But pretty much any question I give you in this chapter will be factorable if it's quadratic. So I'm going to factor this thing. So I usually tweak the equation so it works out kind of nice for you. And so this is a, and that's a, and then you got to have a 2 and a 1. But you got a negative, you got 2 negatives in there. So I'm thinking negative 2 plus 1. So let's backtrack it and see what you think. A times a is a squared, negative 2a, positive a, negative a, and then a negative 2 if I FOIL it out. So what that means is that either a minus 2 would be equal to 0, or a plus 1 would equal to 0, which means a would equal 2, and a would equal negative 1. And it's so tempting to walk away right now, but remember, this was not just a basic quadratic, it was a second degree trigonometric equation. So you have solved the second degree part of it, you've solved the quadratic part. So let's resubstitute in what a was. A was the secant of x. So we have secant x equals 2, and we have secant of x is equal to negative 1. Okay. Now, once again, I kind of like working in sines and coses and tangents. They're easier for me. So I might use some identities now. So I might say, well, at this point right here, I'm going to use an identity. So I'm going to turn the secant into 1 over cos of x, and that equals 2. Now, you don't have to do this. You might realize that secant is r over x. But if I flip this around, I'm going to get cos of x is equal to 1/2. And here, 1 over cos is equal to negative 1. So cos of x is equal to negative 1. So there's what I'm solving for now. More of a grade 11 type problem, but working in radians, so I guess grade 12 here. Okay, so let's take a look at coses being positive numbers. Well, coses are positive in quadrant 1 and 4. So I must be here or here. And I know the x value is 1, and the x is 1, and the r value is 2. So which triangle is that? That one, you've got a 1 there and a 2. Now be careful, because sometimes it's easy to think the 2 is a root 2. It's not a root 2, it's a 2. So this is the 1, 2, root 3 triangle, which means this is the 30, 60, 90 triangle. So if I solve for that, I know that I'm going to have a reference angle here. It's the same as the reference angle here. So my reference angle is the angle it's across from the root 3. And so that's the 60-degree angle, or the pi over 3, the pi over 3 angle in radians. So my first angle is actually, this is angle x. 1 is equal to pi over 3. And my x2 would be 2 pi minus the reference angle of pi over 3. So I've got 6 pi over 3 minus 1 pi over 3 gives me 5 pi over 3. And so now these are general solutions. So to get back to there, I'd have to add 2 pi n. And to get back to there, I'd have to add 2 pi n. N is an element of the integers. So that was the first equation I solved for. So that was that one. Okay. Now comes the next one here. So cos being negative 1, I might use my understanding of the cos graph and say, well, negative 1 would be here. So that's where negative 1 is. So where is that on the x-axis? Well, that is pi. So I would get x equals pi plus, now to get to the next one, you'd have to go 1 whole period away. So that would be the next one right there. So that's a distance of 2 pi. So we'll say plus 2 pi n, where n is an element of I. Now, another way to do this, if you didn't remember the cos graph, would just be to use unit circle again. Unit circle has everything on it. It's so so useful if you know that. So where are we here? There we go. So I'm looking for the place where cos is negative. So remember, you have -1 over 1, right? So this is the x value, and this is the r value. So where on the graph would the x values be -1? Well, that would be at pi. So your angle must be over at pi then. And of course, to go around, you'd have to go pi plus another 2 pi to get back to there. So that's why you're adding 2 pi on the end. Okay, our last question for today. Once again, it's a Saturday, kind of a lazy day. Where are we here? Let's take a look at one where we have to use a different kind of identity here. So where are we here? Sorry guys, just trying to find a good one with a good solid identity here. Not too hard, that's way too hard right now. Yeah, we could try that, I guess. Let's try cos x plus 1 equals sine x. We'll just solve this over the set of 0 to 2 pi. Okay, so right now, if I start rearranging things, it's going to be very hard for me to isolate one of those terms. So I'm actually going to create an identity here. And when I do that, it's going to wind up creating one of these trigonometric equations. So I'm going to square both sides of the equation. Okay. Now, I do need to be a little bit careful about when we square both sides, this idea of introducing extraneous roots. But let's see what happens here. So if I square this, I'm going to get really a plus b squared, which is a squared plus 2ab plus b squared. So this left-hand side is going to give me cos squared x plus 2 cos x plus 1 equaling sine squared x. And you might say, well, why did you do that? Well, one reason is I want to get a single trig term pop out here. So I'm going to use my identity for sine squared x, which is the Pythagorean identity, 1 minus cos squared x. And you kind of got these same things. Let's not be lazy. Let's write them out. So we have cos cos squared x plus 2 cos x plus 1. Let's move everything to the left-hand side now. So if I do that, I'm going to get 2 cos x squared plus 2 cos x. And then I'm going to bring over the other number. So I'm going to be subtracting 1. So the 1's cancel for me. So that's nice. So I get 0 here. So why not, let's factor this thing. So let's factor a 2 out and also a cos x. And that would leave me with a cos x plus 1 inside the brackets. Now, if I solve for this, I could divide both sides by 2. So that's going to get rid of the 2 because 0 divided by 2 is 0. And now let's use our 0 product rule. So cos x would have to equal 0. Because we know that this number times that number is 0. Or the other possibility is cos x plus 1 would equal 0, which means cos x would equal -1, and we saw that in the question above. So I'm going to cheat a little bit and say, well, let's pretend I solved it this way. So there it is right there, cos x equals -1. So I would think the very first time it does this is at pi. So here, x, oh my goodness, x would equal pi. Okay, now for cos x being 0, once again, that's unit circle, because you're saying the x values are 0. because don't forget cos is x over r, right? So we have our unit circle here. So where are the x values 0? Well, the x values will be 0 on the y-axis. So pi over 2 and 3 pi over 2. So either it's here or it's over there. So we have x equals pi over 2 and x equals 3 pi over 2. Okay, just one sec. Okay, so let's finish it off. So we have 3 answers here. Now, I actually squared both sides of the equation earlier on. And so when you do that, you can actually introduce what are called extraneous roots. And extraneous roots are numbers that when you square both sides, they wind up not being true. So for example, let's say you had a number like 4 equals -4. I think we'd all agree that's not true. But if I square this side and I square this side, I get 16 equals 16. And so you would say, well, that's true. So you can clearly see how you can take a statement that's incorrect and turn it into a statement that is correct by squaring both sides. So let's do that with our initial question here. So cos x plus 1, cos x plus 1 equals sine of x. Now, if I test these, I'm going to pause the video and test them quickly for you. You can just check my work in a second here. But you'll see that one of them is wrong. Okay, so here we go. Let's take a look at that. So I just did 3 calculations using the 3 answers. We got pi over 2, 3 pi over 2, and pi. And you'll see the first one actually works out nicely, so that actually is true for us. And the last one works out nicely, that is true for us. But when we plug in 3 pi over 2, we actually get a false statement here. And so what that would mean is that only pi over 2 and pi are the actual solutions for this one. So the questions are a little tricky. We got a lot of different things we have to look at. Sometimes we use identities, sometimes we don't. But I'll leave you with just a few questions to work on and see what you think about that. So hope you guys are doing well. We'll talk to you later.